Let's get started. Like I was making comments, I think the reviews are good. I think people are beginning to ask the right sort of questions and right sort of concerns. Also keep in mind what, you're supposed to find something good in what they're trying to do, right? So keep that in mind, because all the work you're going to find, one level, you can just agree with whatever they do and then kind of move on, which is not what we want. At the next level, you want to be able to complain what they're doing, which is sort of the next step. But the third step would be to kind of put things in perspective, right? Like there are some complaints, but try to see what the balancing counteracting force. So there are no bad papers, there are no good papers. There are papers which do trade-offs, and that's essentially what we're trying to do here, right? And there's nothing in the system, nothing. So some people, I think, like argued, they're kind of hedging, right? Like nobody says threads are it, or events are it. They kind of go back and forth, and that's the reality, right? You can always find some cases where threads are awful. You can always find some cases where threads are good, and vice versa. But overall, you're trying to see what is good for everybody, and that's the hard problem. How do you argue? I can argue how threads are the thing for me, which is sort of where they can say. They can say, I've written threads and events program. I found threads to be very useful. I found events to be very useful, and because I'm John Ousterhout, and I think many of you may not know who John Ousterhout is, but so I'll say a little bit about who he is. But he can say, I'm John Ousterhout. So if I in my career I found threads to be useful, then there's something to listen to, right? So are there any overarching? So before we go, so far we kind of looked at how we organize the operating system, how the microkernel, the monolithic kernel, and all those, how the organization stuff, right? So now we're going to get more into detail about the techniques that operating systems use. And if you took undergraduate operating system, I think you covered 4 different topics. You cover processes and threads and scheduling, as how to give this processes to, how to allocate processor resources. Then you worry about how to allocate memory resources. You worry about how to allocate the storage resources, file systems, and all those things. Then you also worry about how to do synchronization, which comes with the process stuff, right? And I think one of the things I stress in undergrad classes, the synchronization is not exactly operating system. It's basically what happens if you use the operating system primitive, which is threads. If you write a thread program, you will run into deadlocks, you'll run into all kind of issues, and this is how you would solve them. So it's sort of in systems, it's sort of in operating systems, even though it's not exactly operating system kind of concept, right? So for the next few lectures, we're going to look at the notion of CPU processes and threads and stuff like that. So I assume that you know what CPU is, you know what thread is, you know what synchronization is, deadlock is, and all those things. We're not going to cover what those are. You should have gotten them from undergrad. What we're trying to look at here is, we know threads. So now we want to know what is involved with threads. What is the implication of threads? You're probably taught that threads were a lightweight process abstraction, but it's a lot more involved than that, right? And so what we're going to look at that. So the first set of papers, we had 3 papers. This is I think the only time when we read 3 papers, but I think these 3 are so kind of interrelated, there's no point in splitting them. And especially the Ousterhout one is a keynote speech, so it's not exactly a paper, right? But keep in mind, when you read this stuff, keep the chronological order in mind, right? So this was done in 95, 96, and this was in 2001, I think, right? No, this 2003, this is 2002, right? So the order in which it would have happened was that, this, and this, right? So the way of thinking, you have to look at it from that perspective. So for example, Ousterhout would not know anything about what these 2 did. These 2 should have known what the others should do, right? So if Ousterhout never talked about what Adya published, that's to be expected. He preceded them by a lot, right? So 95 time frame, things were a lot different, right? The PCs were sort of taking up. How many of you remember 95 world around 95? So what is the dominant operating systems? DOS. Windows 95 came out, right?
Windows NT was out, NT4.
Yeah. When did it come out, NT?
Yeah, it came out about 94.
Okay. Yeah, Windows NT came out. Normal users would probably use Windows 3.1 or Windows 95, right?
It was NT4 96, because it was after 95. I think it was copyrighted.
Yeah, NT3.1, I believe was the.
Yeah, so there's some sort of a windowing kind of system, some sort of a desktop with the, I mean, I think personal computers are becoming sort of useful, right? I mean, that's sort of the takeaway message, right? Windows 95, I think, was the first sort of, good system compared to Windows 3, which is a lot more buggier, right? And in terms of the Mac, I think they were using the pre-Mac OS X, the classic Mac. I forget what the version is at that time, right?
Windows 7.
Windows 7? Mac 7?
Yeah. Okay,
so probably Mac 7, right? And Linux was out, I think it's like 92, 93. So Linux was probably pre-1, 9.98 or something like that, right? So Mozilla, I think, came out, but hasn't taken off fully. Mozilla was in the Linux kind of world. So when they're talking about the stuff, threading and all those concepts were not exactly in everybody's machine, right? Threading was in the mainframes or whatever. There are a lot of bugs and everything, because I don't think anybody was like dying for threads on those machines, right? There's a single processor machine for the machines that people were most likely to use. They were not multi-threaded, and windowing systems are kind of coming on. So some of the observations he makes that threading systems are buggy makes sense then, right? And what the Eric Brewer and folks kind of point out, it may not be true right now, because we've had a long time to work on the bugs on these things. And the other thing is, most of our machines are multi-core, right? So you demand threads, because otherwise without threads, you don't get the performance benefits of having multiple cores on your desktop, right? So some of the concerns they had probably went away, right? To give you a sense of who these authors are, right? Ousterhout, he did a lot of stuff. He did a lot of stuff in distributed systems, but he's the guy who developed Tickle, right? The scripting language Tickle, TCL. How many of you used it or heard it? Tickle TK. Few of you. It was a very popular kind of scripting language. I think it still is popular, right? And I think now Python may be a better kind of stuff. He did it because he found he needed a scripting language for running some experiments and stuff. So he just created this language, and it kind of took off, and it's pretty popular, right? He's a faculty at UC Berkeley, and he did a lot of stuff on the file systems and distributed systems. We'll see some of those papers. But so when he says he ran into a problem with the threads and stuff, part of his developing Tickle includes and all the other systems that he built, right? Eric Brewer, PhD from MIT, faculty at Berkeley. He's a guy who did Ink2Me. Ink2Me search engine. How many of you heard of Ink? I don't know who owns it right now, right? It used to be a popular engine, and then somebody bought it. I think it's still around, but it's bought by a couple of people. So you might have seen this little logo called Ink2Me. I forget who the current owner is. So, but this was back in the days was a big internet-based service. One of the pre-Google day kind of search engine, right? So he has experience when he says we've done, and then he wrote, of course, a lot of papers in the academia. So when he says we have experience with all the stuff, that's the background where he comes from. Both in the academia in terms of research and in the industry in terms of building large-scale systems, right? And then, of course, these two folks are from Microsoft Research. We'll see many of them. I don't know how much of them in this paper, but in the intersections of these groups with different people, right? So the hope is these people are working in Microsoft Research, right? So they've done some projects which are in the academia, and hopefully some of the things what they're saying would actually get into the Windows kernel too, right? The way I see it, if these people cannot convince their product groups to incorporate whatever they were saying on the events and thread paper, these two don't have a prayer, right? If these people cannot convince the product group that next version of Visual Basic or whatever should have all the things that they're talking about, we don't have the prayer, right? I don't know how the internal politics of Microsoft Research works, but it's easy to assume that these people would have influence, right? So all these three people are giants in their own world. So that's why we are trying to see what's the issue here, right? So do you understand so do you know what threads and do you know what events are? Have you programmed using threads? How many of you programmed using threads? How many of you, so let me ask the other way. How many of you haven't written a program in threads? One?
Not explicitly,
So 2 of you have not written in threads, 4 of you have written in threads. What about the others? So 2 of you haven't written in threads, 4 of you have written in threads. So what did you guys do?
I have written this question.
Okay, but you have written something in threads, right? So how many of you have never written and looked at a thread program, or what do you mean by a little bit? Like
The basic is called creating a thread and
do you ever look at locking some variables and stuff? So it looks like half of you kind of did some useful thread programs kind of stuff, right? How many of you done event-based programs? A lot more of you, right? So what context did you write the event-based system? What do you do with event-based programs?
I think like Visual Basic or something like that.
Mm-hmm.
I just played around with it. I didn't have to write anything in a production environment. But just,
For the GUI.
yeah.
So what did the others write event-based systems for? Event-based programs?
I did a website with like, clicks for events and stuff like that. GUI.
GUI.
Yeah.
What do you say, website?
What is the website?
Yeah, so is that, did you do the client part or the server part?
The client part.
Okay. So like a web browser kind of thing.
Yeah.
Okay. So GUI is one event-based system people have written. Did others write like a event GUI kind of systems?
I built a software using Visual C++.
Okay.
For the breast cancer treatment.
For the what?
Breast cancer treatment.
Okay.
That uses these events.
Okay. So what did you do with the events?
Like menu clicks and all those
Okay.
stuff.
So GUI, right? So it looks like most of you done GUI, right? So for people who haven't done programs with events, right? So essentially, you set up a event handler. So if you use a IDE like Visual whatever, right, Visual Basic or whatever, the system creates some sort of a table internally, and basically it says that if you click something, right, if you click this button, so for every object it creates a lot of events. This is if you click this button, if you go over this button, if you what have you, it will by default do something, and you can change it by writing your own code. So you can say, if I click this button, do whatever. So if it's exit button, you click it, then you exit the program or what have you, right? And that's the way you program. So when you look at the event-based program, you typically don't find a straight line of code, right? If you print it out, right? You don't usually print out the piece of code, but if you print it out, you'll see lots of functions, right? You'll see a lot of functions, but they're kind of hanging off without anything above them, right? So they kind of look like all these functions. There's a function to, if you press this button, this is what happens. If you move your mouse over the button, this is what happens. If you press the space button over this button, this is what happens, and so on and so forth. But there won't be one logic which says like a typical program, right? Typical program, I call it like if you call a main and you write a whole bunch of linear statements and then you call exit, and you don't see those things here. There is no entry point, there's no exit point. It's kind of sort of implicit in this whole model. You basically have lots of events and you operate on those events, right? And the other place where it's used a lot is in web server, right? So if you have a very static web server, right, not a complex dynamic web server, if you have a static web server, essentially what happens is you make a request for a web page. I read the request, read the whatever page you're looking for, I write it back to you, and I shut off, right? So it's a very simple event. So I can have an event handler which basically reads the next request, right, and tells someone, here's the event. I mean, somebody made a request, and you process it. You process it kind of thing, right? And that's another reason why you use events, because the event is incoming read, and then I pass it on to different people who do the stuff, right? In the simple case, the events are completely self-contained. It doesn't share anything, and it's great, right? So in the case of the static web page, I can say he asked for index.html, somebody asked for blah.html, somebody asked for foo.html, right? So all you have to do is I tell you that particular socket wanted foo.html, read whatever the file is, send it back to the person, right? So you're not talking to anybody. So I can achieve parallelism in a very nice fashion, right? So if I have more processes, the event dispatcher, which is the one which is handing this stuff out, can give it to as many processors as you want. So if I have 3 processors, I give one to you, one to you, one to you. If I have one processor, I give one, and then next one, what have you, right? So in the case when they don't talk to each other, life is good, right? But it's not the case all the time. These threads these events want to talk to each other. So the problem that they run into here is essentially what happens when these events start to talk to each other, right? When they start to talk to each other, there is no notion of locks before, because every event handler is sort of atomic, right? So if I call you, you're not preempted. I don't have to interact with you afterwards at all, because I basically say it's your job to do whatever you have to do and respond back, and life was good. But once you start talking to each other, then you begin to have a lot of the other primitives like locking and all those things, and kind of muddy the thing up, right? And so they're trying to figure out how best for you to get. So why did we develop threads to begin with? What is the reason behind having threads?
Isn't it to allow a program that's got a lot of wait states to go ahead and be broken down to smaller elements that can be processed in parallel, even if
so the main reason was to get parallelism, right? I mean, so inherently your program may have lots of cases where there's parallelism when something is waiting for something, or explicitly there may be multiple processors, right? So you want to get the parallelism, right? So we're trying to understand, and events are also parallel by like the way I mentioned. So if I give these things to different processors, then it could be parallel. So these are both ways of achieving parallelism, both ways of doing multiple things at the same time, and we're trying to figure out what is the best way to go, right? Does that make sense? So the notion of stacks, right? How many of you know what stacks are? In what context? So what is a stack? So what is a stack? I'm trying to pick on people who barely speak in the class, right? So what is a stack?
Stack works on the concept of different, that is last in first out.
I'm sorry?
That is last in first out.
Okay. So what is a stack in this context? When they say threads and stack, right? So what stack are they talking about? Yeah.
When you do function calls, that it keeps the environment of the previous function, and then it pushes when you call a function, it pushes the new function's like scope on top of it, so that when you return, it can pop the top of the stack, and then you can be back to the state that the previous function was in.
Yeah, so that's how normal programs work, right? So let's say you have a normal C program, right? You say you have a main program, and let's say you call A, right? And within A, you call, let's say, B, right? And within B, you finish, and at the end, you come back here, and then you come back here, right? Right. So when you call a function A, you go into A's function, right? And actually, you may come back here, right? So A has a whole bunch of stuff, and within A it calls B. So you go into B, do all the code for B, and you come back, and so this is how your programs are written, right? This is how you write your own programs. So what happens is, suppose you have int I equals 1, and you say I equals 10, right? And then if you say print I, right? So when your program starts, it pushes this in the stack. This is allocated on the stack, not on the heap, right? So there's two places where you can allocate memory. So if you do local variables, it's usually on stack. So it's pushed inside the stack. It's allocated from your stack space. So when you go into A, right, it pushes all the state in the stack, and it creates the local variables that you use for within this function onto your stack, and so on and so forth. So if you look at it, you have the mains local variable. This is how your stack will look like, right? And then your return address, and the local variables for A, and then the return address, and then the local variables for B, and so on, right? As the stack grows this way, and when you come out of the function, it pops back up, right? So that's the data structure that you use, whether you are aware or not. That's how your programs are written, right? it's so normal that we do this, we may not think about it, right? So what happens is when you go from, when you call the function A, right? All these previous things are pushed into your stack automatically. We never explicitly push anything because it's done by your program. So when I come and print I here, I expect I to have the, so what would I print? What do you expect I should print? I said I equals 10 right before I called. You should print 10, right? Unless you modified it through some means, you should print 10, right? That's because when you left this function, you saved all the state, not you, but automatically it was saved for you. So when you came back, it was there, and you wrote your program, right? So your program, even though it looked like it is calling functions, if you draw it linearly, it's basically like here, you know, it's if you change it to a linear program, like a straight line program, it will look like it started from here, started from here, and so on, even though it's calling functions, right? So that's the notion of a stack, right? It keeps all your state of your local programs. And if you look at the homework assignment, I ask you that because that's one thing which keeps, which we'll see in some of the other contexts, right? So how big should the stack be? Have you ever run out of stack?
Stack Overflow.
Yeah, have you ever had a stack overflow? Mm-hmm. So what did you do?
It's just an error condition. That's the way we treated it.
Mm-hmm. Yeah.
Usually get that when you have like infinite recursion or something.
Yeah, infinite recursion is one way you get that, right? So what happens when you do infinite recursion, right? Recursion means every time you recurse, you push your stack, your state into the system, right? So eventually your stack will run out, right? There are ways to get rid of those if you hand code it, and if you do a traditional C, you won't be able to do that. But if it's a special kind of program, you can basically do tail recursion. I think one of the paper mentions that. So if you do a tail recursion, right? So if you say function A calls A of I minus 1, if it does something like this, right? Then it's sort of tail recursion because there's nothing else behind here. So I can kind of purge the stack of this variable before I call because I'm never going to go back here, right? So there's some optimization people do to make recursion still work. But in general, if you do uncontrolled recursion, you'll eventually run out of stack, right? So who allocates a stack to your process? How do you decide what the stack size is? Okay, so stack size are allocated by when your program starts, right? That's one of the things that your program starts up. You have to request the operating system, right? So think back on the undergrad operating system, right? You write a little program, and your compiler would create all these memory sections, but eventually you have to ask the operating system to say, I want something for stack, something for heap. And it's up to the operating system to give you memory, right? It's basically a memory allocation problem, right? So one of the things you might not have realized you were doing that was you ask the process for a certain amount of stack. When you do a thread, you have to figure out how much stack you want per thread, right? You don't typically give it as much stack as how much you would give for a program, right? Why? Would you give the thread as much stack as what you would give your program? Actually, I answered no, so take that as no, and then why won't you give?
Sharing memory space with the thread?
Yeah, I mean, if you create lots of threads, right? One of the things they complain about is if I create 10,000 threads, so I'll have to have 10,000 times the stack space. So your program will be humongous because it's having all the stuff. So you want to give the threads some amount of state, right? So you have all this state that are being maintained, right? And how do you? So your goal is to keep that thread space, the stack space small to reduce amount of state being maintained. But the good thing is now your program the way you normally do. You don't think too hard about it, right? So one of the other aspects is if you put a breakpoint in your debugger at this point and you do a stack trace, it'll tell you that your program came from A at this location. It came from main at this location, right? So you can go back in the stack to see what's going on. So debugging is easy because you know where you came from, right? If I look at a normal program, I set a breakpoint, I know precisely in the logic where I am. I can kind of look at the stack to figure out how many of you used debuggers, right? All of you should use debuggers because I can't know how to program without using a debugger, right? So if you use a debugger, one of the main things you want to know is if something happens, I want to know how I got here. And to know how I got here, I look at the stack. I do a stack trace, or I think they call it trace or what have you, which basically tells you that I came from all this stuff, right? So suppose this was, instead of calling A, it says thread create A, right? So this was a thread creation event. What would your stack trace show? I'm doing a breakpoint here. I'm looking at the stack trace. What would it show? How far would I be able to go up?
You'd just be able to trace it back through the thread, because the thread would have a separate stack there.
Yeah, so you won't be able to look beyond that, right? How many of you done this? If you do this, all you can know is you are in thread A, but you won't know where you started. You won't know that you came off from here. If you haven't seen this, try it out, right? If you didn't have it as a thread create, you'll be able to say that at, let's say, line number 10 is when I call A. So I can say in main function, line number 10, I call A, and A at some point call B, and B, I'm right here. But if you do a stack trace on a thread, all you know is you are started from thread A. You don't know where it was created. So if you have another thread create for A, you don't know whether this is this or that, right? How many of you seen this? So if you debug any thread program, right, and you do a thread trace, stack trace, it doesn't go all the way up. It only goes up to the thread that caused it, right? And usually you know from context what it is, right? But sometimes you don't know. So since it looks like many of you haven't seen those, right? So try it out. It's very easy to do it. Just create a thread and then look at the stuff. So debugging becomes a little bit harder now, right? Debugging in general, how many of you think that debugging is easy and you would love to do that? You have to do that because, I mean, whether you love it or not, because if you want to write a program, you have to debug, unless you are very good at writing a program which runs correctly all the time, right? How many of you use debuggers on a serious fashion rather than just trivially? Very few of you. I'm kind of surprised, right? So if you write any kind of programs, you'll have to use debugger. And one of the things you do with a debugger is, the common thing is you are trying to figure out where I am, like how did I get there, and what's the state around me, right? And you can do a lot of nice stuff with debuggers, but at the least you need to know how did I get here, what is the state, what is the variables here, and all those things, and you can't go beyond the thread, right? That's because you have all this state over here, right? So this is the stuff they're talking about when they say threads and stacks. So when you do a thread, right, you get this linear kind of style of programming that you used to get without the non-threaded stuff, right? So when I write it with threads, I'm able to kind of go back in my stack up to the thread point without thinking about it. I don't have to save any state. So if I had a variable called int b equals 10, when I finish this function, I know I will have access to this b, whatever I sent here, right? You never think about it. You just program it because you know that's how things work. So you know how the stuff. You never had to figure out how to save the state that they're talking about, right? Is that clear? I'm going to go to the event-based system now, right? And I had to erase this stuff. So event-based system, you have a, let's say, like a dispatch function, right? Which says that if I get event A, this is the handler, right? Handler for, right? So if you have event call A, like a read or whatever event you can think of, like in the GUI window clicked or whatever, somebody, the dispatcher, figures out that event A happened. So it'll call this function, right? It'll call handler A, and you are able to do something, right? So if this handler, so it's up to this handler to figure out where it is and do all the stuff it wants, because the way you're supposed to use it is at the end of this handler, you're supposed to return back to the handler this, whatever the resource you're using, right? You are supposed to write a program where it's a straight line code and it finishes, right? What would happen if you wrote while one loop inside the thread handler, inside the event handler? What do you think will happen? Yeah.
It will never end. I mean, you never get out. You never exit that event.
So what happens?
The program crashes.
No
Yeah.
other events will run.
Yeah, none of the other events. I mean, so if you, depending on how you do this stuff, right? If you have 3 processes and you're doing an event using a pool of event handlers, if you had 3 event handlers, this event handler is completely gone, right? If you had only one, then your program hangs because till you get out of the stuff, right? So if the event dispatcher only does one at a time, right? That's the reason why we loved it. I mean, these people loved it, right? Because now I don't have to worry about synchronization because I call this handler to do whatever, right? And then I can call this handler. This handler does not have to worry about shared variables or modifying anything because you are guaranteed that you're the only one who's going to run. So life was easy. But if you do a while loop here, if you don't return, then nothing else can happen. If you do something very slowly here, if you have to read, so if in the case that index.html I mentioned, right? If index.html happens to be a 1 gig file, and you're sitting in a loop reading the 1 gig file and writing it out, till you finish, nothing else can happen, right? So if you wrote a web server based on this stuff, then you can have horrible performance, right? Because it's good when the operations you have to do is very small. It's not good if you have to do lots of complicated operation, right? So you have a little bit stacks. If you ever debug the event-based system, all you see is you can do a stack trace only up to here because your stack is cleared before then. And any variable you use has to be here. And when you're done, you have to save it somewhere, right? If you want to keep a count of how many times index.html was used, you can't have a variable called index.html count plus or something, unless it's a global variable, unless it's stored somewhere else, not on the stack, because your stack is purged all the time, right? You may have been aware of it, may not have been aware of it. You may have been okay with it because of the scoping rules. You may assume that within the scope, it's not available, so your programs were fine, and you are probably okay with when you write simple programs. But the complicated programs, you don't want these things to be looping. So what you do is, if you have to do something which takes time, you create it, you let it run parallelly using a process or whatever abstraction, and then when it finishes, you call that an event, right? So here's what I would do, right? So suppose when I get a read request for index.html, right? This is an event, right? I call the handler, right? This is how I would have programmed it, right? So it has to read index.htm, right? And then send Can you see what I'm scribbling basically? But so the handler here would have, when it comes to the handler, it knows that you're asking for index.html. So it would have passed you that somebody is asking for index.htm, right? So your code would have read this from the disk, right? So let's say read disk, right? You read this from the disk, and then you send it through the network or something, whatever you read, to the destination which would have been given to you, right? This is how you do a program. See, if you did like this, your program would be terrible, right? Because while you're reading this stuff, everybody has to wait. While you're sending this stuff, everybody has to wait, right? So that's the problem they're talking about. So what you do is you rip this program to say schedule read index.htm, right? The assumption is when this operation finishes, so then you return, right? So when this read finishes, you will have to have another one for read file, another event handler for read file. You will create another function here, which will get the data, right, and will schedule send with this data, and then it will return, right? So you rip that one function we had with two of these operations into two different stuff. So basically now when I do this read, schedule this read, right, I'm letting something else go on and do this operation by itself. I mean, do the stuff. When it finishes, it'll cause an event, which will call the event handler to say, I did a read. I finished the read, so now I get this do what to do. And I schedule this send event, send, which is like some networking code, let's say. And then when that event finishes, something has to happen. So if you want some notification, then the send event will say, notify done, right, to somebody, and then you finish, right? So now you ripped apart this one function into three different functions, right? So that's that's what they say, they talk about ripping, right? So why did they call it stack ripping? This is from the Adya paper, right? So suppose in the case of here, right? Suppose you had int count equals x, 10 or something, right? How would this be in the previous case? When you had a read and a schedule, this count was available within the scope of this whole program, right? Basically, the C program you had the scope, right? So if you want this count for sending, right? You want to send something with a send. How do you do that? You can't have it in stack anymore because when this handler finishes, this is gone, right? So it's up to you to put it in heap, or other words, global variable, right? You have to allocate a global variable call something, put this in there, right? So that when this event handler runs, it will know what to get, right? More importantly, this one has no clue how it came here. If you wanted to know how it got here, you have to send it something, right? So in the logic that you initially had, you had a read, send, right? And then you finish it, right? This is the original event handler you had. So this read and this send sort of know by the logic where they belong, right? So this send, when you write in the code, knows that it's trying to send whatever is read here. So they know what is going on. Whereas in this case, this send is complete. So when you get the event for send, when it says like, when you had the event for it's been read, this handler has to know that it is part of this logic two-step process. I'm in the middle of the second process. So now I have to go and find out where I have to go, right? Right? You can't even have if you want to do this, you can't have a global variable for count. You have to have the global variable which corresponds to when I started the read, not when I did that one global variable for handler. Does that make sense? If I were to rip this code, right? If I were to rip a code which says int count equals 10, right? The third handler for send should know what was the value of count when the person who scheduled the read for my particular handler did. So it's possible that another version had count equals 20 and then read and send. If you had these two handlers and if you rip them apart, right, they'll both do the same this function, right? But it's up to you to tell this one that if you came here because of this handler, your count variable is 10. If you came here because of this variable, your count is 20, right? It's entirely up to you how to do that, right? You have to keep track of, so you're managing this thing, you're managing all the stuff that you need, and that's what they're complaining about in Adya paper, right? You have to manage the stack. You'd probably never called it managing stack, you probably called it maintaining the state, but you have to keep track of all the state because when you call this event, you have no idea how you got here. And if you want any kind of state, if you want any kind of history behind how you got there, you have to keep all the stuff in mind, right? Yeah?
But wouldn't things like the count variable, couldn't that be passed to the handler? Parameter?
No, because the calling is done by the next event, right? So the event handler has to know that the state, right? So you could change it to say all your functions will get this user-defined chunk of memory that will always pass around, right? But in general, all you do is, if I rip it into this function, right? I schedule this read, then I go away, right? The person who's going to call this actual handler is the event dispatcher, right? It does not know about your program, so it does not know that it has to pass count or what have you, right? So all it does is when it has the event, it calls somebody, right? It doesn't remember all this trace of event, because that's the beauty of the event handler, right? The event handler, all it knows is somebody clicked on the button, call this thing. It does not know that somebody clicked on this button and I'm in the middle of like a complex processing, so I have to keep track of all the state, because if you do, then the whole thing is a mess. I mean, the whole thing slows down. But here, it's a simple thing. Anything, some button click, I call this, this, I do this. So I get an event for completed read, right? Somebody said I should do this event, so I go here, right? But managing the state becomes really messy, right? So if you've written anything complicated where you have to rip this function like that, your code would be completely bizarre, right? There must have been another case where you've done this. How many of you done RPCs or remote procedure calls or RMI in Java? So you must have done the same thing, right? So if the whole notion of RPC is I can call this function which looks like it's local. All of you have used RPC, right? Because when you use many of the system calls, they internally call RPC. But explicitly when you call RPC, right, it looks like it's a function. It looks like I can call a function, but it's really on the other side, right? So when you have two machines, I call this function call A, and I'll get a return value right here, right? But what really happens is it gets pickled, all the arguments, everything are packaged up. So it's sent across to another machine, right? And some dispatcher figures out that there's a function called A. It calls it all the arguments that you passed, right? And changing in the machine, little endian, big endian, all those complicated stuff. And essentially does all the stuff for you and returns the value back to you, right? This is the notion of the RPC, right? For it to work, you have to, so it's supposed to be transparent, right? You're supposed to be able to call A and then everything should get done, right? But if you so it's possible that you wrote A to be in this function. Somebody could have just carved it out and sent it to a remote machine and things should work, right? Except if you call a global variable here, and if you move it over here, then you won't have the stuff, right? So if you're writing remote procedure call, it has to carry all the state that either you explicitly or implicitly use. If you implicitly use some global variable here, that will fail because the state didn't go through, right? So when you write RPC programs, you constantly evaluate that because you look at the code, you go like, well, I set the variable here, but then you have to remember that whatever globals you're using is not available on the other side. You have to pickle it, you have to send everything with the stuff, right? And the simple answer is, why don't we send every state with every call, right? And obviously, that's an awful thing because then your program would be completely so because it's sending the whole memory back and forth, right? It's the same kind of problem, right? You want to get all the benefits, but the event-based system, if you do any kind of this stuff, things fall apart, right? So where they start, where the assumption of where the whole thing starts is, this is the world, right? Yes, event handler is beautiful. When you write simple event handler for GUI and stuff, you probably didn't have to think about any of the stuff. You just had this event handler for close, open, and all those things. Button, you wrote the program, things were fine. But if you did anything serious with event handlers, right? If you wrote, let's say, the PowerPoint application, right? Your event handlers are doing more stuff than just exiting the program, right? So if you do a spell check, it has to do a spell check, which means that it cannot freeze up the entire system while it's doing spell check. It has to rip the stack which you never call it rip the stack. You basically say, I schedule another event kind of thing. But very quickly you find out that this whole thing gets messy, right? The other problem is when you have a code like this, it looks sort of easy to see. When you rip it apart, you can't say the new event handler should come right here, right? Because that's not how C works. You can't just randomly go into the middle of a function. So you have to make that into double functions, right? So in this example, now I have event handler for the main one, I have event handler for the schedule part, and maybe perhaps an event handler for the notify part, right? So now I created 3 different handlers for the single function, right? In case you decide to change something, now you have to go revisit everything. You have to revisit to see what was sent, all the stuff. So you can't just modify the program just like that, because if you change it to make this read into 2 different events, then you have to remember to do the whole thing over again across the whole thing, right? And somebody has to understand the whole thing. So now the logic that you used to have, which is this is the logic you used to have, now spread all over the place, right? And all of them basically right off of this table, right? So now we have all these events. So you have to remember that even though I see 3 different event handlers, they're all part of logically one construct where one follows in a certain order, which is completely lost here. So when you look at this stuff and you're debugging this stuff, it becomes messy. Because if you're debugging this stuff, all you get here is it says that you started from here. You have no idea that this is in the middle of an operation, right? It's middle of operation where you are in the middle of the operation, you're doing something. So debugging this is complicated, and all the things they complain about, that's the context of it, right? Yeah.
When I've run into that before, what you end up doing is you find yourself calling each of the handlers by a different name: read A, read B, read C, read D.
Mm-hmm.
So at least that way you know which function you called when there was a problem. But it gets to be real messy programming.
Yeah, so that's a classic way of doing this stuff, right? Which the one way, if you don't know what's going on, is now you have, instead of having one read handler, you have n read handlers, right? So if you know read A, that means it came from here, right? If it came from there, you're going to call read B, this way read C, this way read D. So now you have n different functions which are all the same, except they have different names because that's how you're debugging, right? And if any of you have programmed like that, you'll know that it very quickly becomes messy, right? Because then you forget that you had all this stuff, you never put it back, then you have all these things diverging because that's how we program, right? So the whole bunch of mess, right? So event-based programs are very popular within, I think, the Windows community, right? I mean, if you use Visual Basic, Visual things, they make event-based systems very easy to use, right? Unfortunately, many of you haven't programmed in either system, but if you do program, so how did you guys program if you haven't done threads or event-based system? Was it like straight line code?
Multiprocessor.
How did you write the multiprocessor?
Fork and exec.
Fork and exec, okay. Okay. Fork would face the same kind of issues that we're talking about here, right? If you do a fork, you get to see up to your main, not your previous stuff, right? It behaves like a thread, not like here, right? Because when you do a fork, when you fork program, something happens, you can't figure out how you got there, right? You only know that you're running and you go from there, right? And one of the ways you debug is similar to what he mentioned. You call it different programs. You say fork, fork A, fork B, fork C. So so if you're calling the same program 10 times, if you want to be able to debug, you could call it the first time fork 1, second time program 2, or something like that, right? So for the rest of you, when you try to write more complicated programs, you have to deal with this stuff, right? You have to deal with this stuff because these are elegant ways to get multiprocessor capabilities, but the challenges are hard. And more than when they realized, unfortunately, this thing does not remember any of my settings. I don't know why, so you can't change this in. Anyway, so what they're saying about is very important because this is how normal human beings program, right? So normal human beings, I'm assuming in Windows, they use event-based system because that's what they've been pushing, sort of thing, right? And how do they get good performance? How do they get this stuff? And they're trying to understand what's going on, and that's the context of what this is. There's a lot of fight going. This. If you look at the references, right? This has been ongoing since late 70s and stuff, right? How many of you believe that these people have addressed the different issues and they should move on, right?
That they should move on.
We should. Like I'm saying, the problem is solved. Let's go with threads or something, right? How many of you believe that the problem is solved? How many of you believe that it's still not clear? Yeah.
Well, it seems that I guess the second paper there, in 2003 event, addressed a good point when they said it was basically solved in the 70s. When they said that they're basically the same thing, and you know, it's just a matter of what works best. But the problem is that we still don't know what works best in what scenarios.
Yeah. So that's an interesting point, right? The paper we didn't read showed that they're both equivalent, right? Is that the answer, right? To me, the equivalency means that they're equivalent, right? They're equal, let's say equal power to do something. It does not say anything about which is easier to work, which is practical. I mean, that's a theoretical concept of equivalence, right? I mean, whatever you can do with one, you can do with the other, right? That's good to know, but we're not trying to, I think that's good, but we need to know which one is easy to use, right? So I don't know how many of you knew this is how event-based systems really have to work. If you knew this is how it really works, would you say event-based systems are easy to use?
Again, it depends what you're trying to program. If you're trying to program a GUI type interface, it's a heck of a lot easier to program it in an event-driven system than in a thread-driven system.
Okay. But if you get more, so if it's a simple program, event-based systems are fine, right? If you have to do more complex like ripping and stuff, then it's not so clear. Which is what Ousterhout said, right? I mean, Ousterhout basically, he did not say that threads are, you shouldn't program in threads. He just said threads are pretty complicated. Threads are not an easy thing to use. So don't do it unless you have to, right? So for normal stuff, just for normal little programs, just use event handlers and move on, right? I would argue that he also said, though, even though he didn't articulate it, don't rip, right? He would have said use events, and if you have to wait and stuff, you have to do reads and stuff, your program will be slow. That's fine. For normal programs that you're going to do, that's perfectly fine, right? But if you're doing any kind of high performance stuff, like I'm assuming that if you're working on grids and stuff, you're worried about performance, then you have to bite the bullet and deal with threads, right? And threads are a bear. So they say, one of the things that Ousterhout says is threads are very hard to use, right? Many of you haven't programmed in threads, but let's say for the people who program in threads, how many of you think threads are easy to use? The answer is threads are easy to use depending on what you're trying to do, right? The simplest way to use a thread is you put the whole thread inside a monitor, right? How many of you know what monitor is? You have to know because that's required, right? You know what a monitor is, right? So what's a monitor? What's a monitor?
Monitor.
Yeah.
We can see the output from.
No. I'm saying the monitor, like the thread, the synchronization primitive monitor. One of the synchronization primitive, not in this thing, right? But the synchronization primitives are, what are the different synchronization primitives that you, what are the different synchronization primitives? Who wants to? That's from undergrad class, so not from this lecture, right? So what are the different synchronization primitives? Yeah.
Semaphores.
Yeah.
Mutex. Monitor. Fairly close.
So what is a monitor?
It's a way to lock a function or some data structure so that when you go in, it's atomic, and then when you exit, then it becomes free again.
Yeah, so you need to. Yeah, so you need to read up on what those are, right? Because we're not actually explaining those, right? So monitor, you say the whole thing, right? So monitor, you don't have fine-grained notion of saying, I want to lock this piece of code. You basically say the whole thing, right? So I can create the whole thread inside a monitor, which means that the whole thread, only one thread can run. There's no interleaving. There's no synchronization issues. So that will solve the problem. So that's the easy way to write a thread program, but I put the whole thing inside a monitor, and my program is fast to write, but if performance would be awful because you're essentially kicking everybody out. You want to be able to do fine-grained locking of individual data structures. So that is not a trivial task, right? And so let's look at some of the stuff that people actually talked about. And again, the notion of why do we care about this whole thing? Because this is how you get concurrency, right? This is how you get concurrency, and you pointed out this is how you use your multiple processors or what have you. If you don't address this issue, then essentially you're going back to a single processor machine. And as the hardware folks will tell you, they can't keep making the single processor machine faster and faster, right? So the future is multiple cores. The future is going to be, you're not going back to a single core anytime soon. So if you have multiple cores, you have to be able to use all of them. That means if you want to get the performance for interesting program. So clearly, if you want writing hello world program, you don't care. But for any normal program, you want to do this stuff, right? In that context, actually, I find the Google Chromium to be pretty interesting, right? How many of you kind of followed what they were trying to do with the browser? Yeah.
They ran every tab as a separate
process,
right?
Yeah. So one of the nice things is they're running every tab, which is sort of like the window, right? Every window in a browser to be a separate process, right? So they can avoid, so the memory leaks and all those things they're avoiding. So essentially now you have a process. So the Chromium is basically a process spawner, right? You can have multiple processes failing. So it's awfully sounds like a OS built on top of a OS. I mean, it doesn't do certain things, but it's getting kind of close there, right? So anyway, so one of the nice things is if you have multiple processors, you can assume that the processes will be scheduled in different processors, so you get to use it. Yeah.
I found some of the applications slower in the Google Chrome than Mozilla Firefox.
Okay, so why would that be?
That's what I mean. If
so I'm asking the class, right? Some of the what slower?
Like I wanted to play chess on Yahoo.
Okay.
And I opened in a new tab.
Okay.
And I thought it should be faster than like Mozilla Firefox, but it wasn't.
So how many of you want to guess why it's? So in Chromium, every time you open a new tab, you fork a new browser and you run something in there, right? And the idea here is memory leaks won't affect you. If the tab crashes, it won't affect you. But sometimes the new tab is slower than Firefox. Firefox is not multi-threaded, right? So why is it slower?
Probably because all the plugins and everything that it's using has to be initialized and in each process so that it can do something.
So the startup time would be slower for Chromium, right? That's what you're saying, right? The startup time would be slower because each browser would have to load all the new stuff, right? So that's one component, right? What's the other one? What's the difference between multiple processes and a single process with stuff? Yeah.
The scheduler. Whoever's scheduling is going to be different. So when you're doing it in Firefox, the scheduler is going to be Firefox, whereas if you're doing multiple processes, the scheduler is going to be the OS.
Yeah, so that's another excellent point, right? So now you assume that the OS is giving you the right way, but that assumption need not be true, right? So if you create two processes, you assume that the two processes would get better than what the one is partitioning among both of you. It need not be true all the time, right? What about memory sharing? What's the memory page cost for process versus same? Two different processes versus same process. You're also assuming that sorry.
I was just going to say you can end up with memory conflicts, but wouldn't they both have their own sort of fenced-in memory?
So when you have a single Firefox, it does not have to be fenced in. It's up to you to fence it, right? You have a single process, so it's up to you to fence it whichever way you want. But when you have two processes, you leave the control to the operating system, right? So a previous iteration of your chess program may have left some data which may have been used in the Firefox better than it could be in Chromium, right? I mean, there are cases when splitting into two processes is good, but if they are sharing something, if they're using something explicitly or implicitly, then having a separate process means that now you have this firewall between them, and you're leaving everything to the operating system to deal with. You don't know what happens, right? And also, Chromium may just be slow. I mean, nobody says the Chromium, each process is faster, right? So maybe it's slower than Firefox. So there's a lot of interactions happen, right? But anyway, so the idea here is to use multiple processes, and that's what you're trying to do, and that's why you want to worry about this. So whether you like it or not, these are the the ways of doing multiprocessor kind of programs, right? Fork is another way, but fork has, I mean, you don't share anything at all. So creating shared memory and everything becomes much more complicated. So you either write threads or event-based system, and the threads stack, when normal people don't call it a stack, they just know that when you think about a program, it's one linear-based system. Whereas in events, you only think about the event handler. You're told not to think about where it comes from and all those things. So you write this event handler assuming nothing, right? Assuming nothing is, whatever is given to you through the arguments, and whatever you want to do is what you do. You cannot assume that this thread handler has to come after this, that after before is up to you, not to the system, right? So you need to write some things. So when you look at when you're trying to debug these things, you get different kind of behavior. This one you only see where you are, not how you came from, and threads you get a little bit more. Yeah, again, Ousterhout wrote technical language, so he sort of is in the space a little bit. So his point is, threads are very hard to program, right? They're painful. Even for experts, they are painful. So don't do it unless you really want to feel the pain, right? Because you have all these issues that you have to deal with. One is the synchronization, right? And synchronization and deadlocks and all those things. And if you use a monitor and protect the whole thing, you have no bugs, but the system crawls. If you want to do a fine-grained stuff, things are good, but you pay the price, right? And incidentally, this is what all the programs that you're using do, right? When you go from, when your kernels become more and more fine-grained locking than they used to be, right? Windows 95 is not multi-processor, but if you look at Windows XP to Vista, internally that's what they have to do, right? Make the locking more and more fine-grained, so you only lock what has to be locked, right? And really, what you have to do is, if you have variables which look like they're shared, but by the logic they'll never get to each other, right? Then you don't lock them, right? So suppose you have one shared variable which is used by the open function and the close function, right? If you know that there is no way they can both be done at the same time, you don't lock them, right? So you need to understand the logic. So you need to get best performance, you have to avoid locks as much as possible and lock the least amount of stuff, right? So you get the maximum performance and your program becomes impossibly hard to debug, right? So you have to balance those stuff, right? Debugging, otherwise it's also hard because you have a lot of data dependencies, right? And you have, the worst part is timing dependencies, right? If any of you program with threads, that's one of the things you realize, right? So threads means that now you have both of them going at whatever speed they want to go, right? So when a bug happens, it depends on what everything else in the system was doing, right? And when you try to run it under a debugger, you perturb the whole system because now the system is going slow, everything works fine, right? So if you're single stepping through the program, everything is fine because now they're doing baby steps, things are fine. But when you let them go by themselves, they run into each other. So when you run into synchronization problems, it's not a trivial way to figure out what happens. It depends on the timing. It depends on who ran faster than the other one. So you have to look at all the possibilities. So if you try to think of this, it's a very complex mechanism to get that, right? It breaks abstraction because now if you have multiple threads, you have to figure out where the threads are and what they're doing. So instead of having one linear program, now you have multiple things going all up at the same time. So now you have to say, I need to do multiply a matrix, divide a matrix, but they both are running in parallel. So I have to kind of know what the other one is doing. So I can't write this multiply by itself. I have to assume that the divide is running parallel to me, and I have to use as much cases where I don't have to lock, because if I lock everything, I slow down. So that's a very tricky thing. So again, that's the key. So fine locking is good. Everybody knows fine locking is good. That's probably what you are taught, that fine locking is good. But getting it right is extremely hard, right? I bet that you still have bugs in Windows Vista code base inside the kernel on this locking issues. And you notice it sometimes. Your machine locks up, right? And which is how you see it in the user space. Essentially what happens, right? And threads are not well supported back then, but that's not true, right? Event-driven programming, in the simple case, it's trivial. It's trivial, right? You call this function, what have you. But when you have long-running handlers, what the Adya paper calls as stack ripping, you have to do that or your system slow.